Hello everyone. Today we are going to talk about MotionLM, multi-agent motion forecasting as language modeling. The motivation for this research is to enhance interactive motion forecasting. The current methods in use have limitations, particularly in their ability to effectively handle interactive prediction challenges. These existing approaches often struggle to capture the joint distribution over multimodal futures, which is a crucial aspect of accurate forecasting. The approach that this research proposes is unique in that it leverages multi-agent rollouts over discrete motion tokens. This is a significant departure from existing methods, which may not generate a sufficient number of samples to represent the multimodal future distribution. This limitation in existing methods can lead to less accurate predictions and a lack of comprehensive understanding of potential future scenarios. The proposed method in this research addresses these limitations by using rollouts to aggregate data. This approach allows for a more robust representation of the multimodal future distribution, leading to improved forecasting accuracy. The number of rollouts generated is varied, but always clustered down to k=6 modes for evaluation. This method has been shown to surpass the previous top entry on joint map with just 32 rollouts, demonstrating its effectiveness. In conclusion, while existing methods have made significant contributions to the field of interactive motion forecasting, they have notable limitations. This research proposes a new method that addresses these limitations and offers a more accurate and comprehensive approach to forecasting. The proposed method's effectiveness is demonstrated through its improved performance metrics and its ability to establish new state-of-the-art performance on the WOMD Interactive Prediction Challenge. The existing methods in interactive motion forecasting have been facing challenges in effectively handling the interactive prediction tasks. These methods often struggle to generate a sufficient number of samples to accurately represent the multimodal future distribution. This limitation is significant as it hinders the ability to capture the joint distribution over multimodal futures, which is crucial for accurate forecasting. The authors of this paper aim to address these issues by introducing a new method that leverages multi-agent rollouts over discrete motion tokens. This approach allows for a more comprehensive representation of the joint future distribution. The number of rollouts generated is varied, but they are always clustered down to k=6 modes for evaluation. The method uses 512 rollouts per replica for final leaderboard results, but it has been found that even 32 rollouts are sufficient to surpass the previous top entry on joint map. The proposed method has shown significant improvements in performance metrics, which generally increase as additional rollouts are utilized. The model with 9 M parameters is used for the main results, which performs decently. However, a model with 27 M parameters tends to overfit, while a model with 300K parameters underfits. The authors also conducted an ablation study, varying interactive attention frequencies and numbers of rollouts. The study evaluated single replica performance in addition to the ensembled model performance and computed standard deviations for each metric over 8 independently trained replicas. The key improvements introduced by this method include the ability to better capture the joint distribution over multimodal futures and the flexibility to adjust the number of rollouts used, which can significantly impact the model's performance. The authors also suggest potential avenues for further improvement, such as leveraging the trained model in model-based planning frameworks and exploring distillation strategies from large autoregressive teachers. These strategies could enable faster student models to be deployed in latency-critical settings, further enhancing the performance and applicability of the proposed method. Section 1. Problem formulation and approach. The authors of this paper have identified a need for improved interactive motion forecasting. They have formulated the problem as one of capturing the joint distribution over multimodal futures. Their approach is unique in that it leverages multi-agent rollouts over discrete motion tokens, which allows for a more comprehensive representation of potential future scenarios. This is a departure from previous methods, which may have struggled to adequately capture this diversity. Section 2. Methodology and experiment design. The authors have designed a method that uses rollouts to aggregate data, with the number of rollouts generated being varied, but always clustered down to k=6 modes for evaluation. They have conducted experiments using a model with 9 M parameters for the main results, which performs well. They have also tested models with different parameters to understand the impact on performance. The experiments were designed to evaluate the model using performance metrics, which generally improve as additional rollouts are utilized. Section 3. Improvements and innovations. The proposed method establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge, demonstrating significant improvements over existing methods. The authors have also identified potential avenues for further improvement, such as leveraging the trained model in model-based planning frameworks and exploring distillation strategies from large autoregressive teachers. These innovations highlight the authors' commitment to continually refining and improving their approach to interactive motion forecasting. Technical results. 1. The proposed model has established a new benchmark in the WOMD Interactive Prediction Challenge, demonstrating its effectiveness in interactive motion forecasting. 2. The model's performance metrics generally improve as the number of rollouts increases, indicating the importance of generating a sufficient number of samples to represent the multimodal future distribution. 3. The model has shown competitive results in WOMD marginal motion prediction, ranking second in the main ranking metric of softmap, and achieving a significant improvement in miss rate over all prior works. 4. In the interactive motion prediction, the model has achieved state-of-the-art results, with a 6% relative improvement in map and 3% relative improvement in miss rate over the previous top-scoring entry. Implications of results. 1. The results indicate that the proposed method of leveraging multi-agent rollouts over discrete motion tokens is effective in capturing the joint distribution over multimodal futures. 2. The improvement in performance metrics with the increase in rollouts suggests that the model's ability to generate a sufficient number of samples is crucial for its performance. 3. The model's success in the WOMD Interactive Prediction Challenge demonstrates its potential for application in real-world scenarios involving interactive motion forecasting. Ablation study results. 1. The study involved varying the number of rollouts generated, but always clustering down to k equals 6 modes for evaluation. 2. The performance metrics were observed to improve as additional rollouts were utilized. 3. For the final leaderboard results, 512 rollouts per replica were used, although it was found that 32 rollouts were sufficient to surpass the previous top entry on joint map. Implications of ablation study. 1. The ablation study results reinforce the importance of generating a sufficient number of rollouts for the model's performance. 2. The findings suggest that while increasing the number of rollouts can improve performance, there is a threshold beyond which additional rollouts may not significantly enhance results. 3. The study provides valuable insights for future work, including the potential to leverage the trained model in model-based planning frameworks and exploring distillation strategies from large autoregressive teachers. Key highlights of the paper. 1. Key insights. The paper presents a novel method for interactive motion forecasting that significantly outperforms existing methods. It emphasizes the importance of the number of rollouts used, as it can greatly impact the model's performance. 2. Key contribution. The paper introduces a method that leverages multi-agent rollouts over discrete motion tokens. This approach is able to capture the joint distribution over multimodal futures, a task that existing methods may struggle with. 3. Key idea. The core idea of the paper is to use rollouts to aggregate data, with the number of rollouts generated being varied but always clustered down to k equals 6 modes for evaluation. The method uses 512 rollouts per replica for final leaderboard results, but it is found that 32 rollouts are sufficient to surpass the previous top entry on joint map. 4. Key results. The proposed model establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge. The model's performance improves with the increase in the number of rollouts. A model with 9M parameters is used for the main results, which performs decently, while a model with 27M parameters overfits and 300K underfits. 5. Key conclusion. The paper concludes with the potential for future work, which includes leveraging the trained model in model-based planning frameworks and exploring distillation strategies from large autoregressive teachers. This could enable faster student models to be deployed in latency-critical settings.